The BJT can function in one of three modes of operation. In linear mode, it works as a current amplifier. In saturation mode, it resembles a closed switch. In cutoff mode, it acts as an open switch. Each one of those modes has its own model, its own equivalent circuit to represent the BJT. Let's remember what they look like. In linear mode and DC, the transistor and NPN is represented by a very simple circuit. One voltage source that ensures that the base is higher than the emitter by 0.7 volts, and a control current source that represents the current gain characteristic of the transistor. The collector current is beta times IB. Beta is the current gain, which appears sometimes in manufacturers' data sheets as HFE with uppercase F and uppercase E. If you find it with lowercase f and lowercase e, it means something else. In cutoff mode, the equivalent circuit is even simpler. An open circuit between the base and the emitter, and another open circuit between the emitter and the collector. Finally, in saturation mode, there is no current amplification. The transistor merely maintains the collector 0.2 volts higher than the emitter, and the base 0.7 volts above the emitter. The question is, how do we know what is the mode of operation of a given BJT? It's easy. The first thing we do is we replace the BJT by its equivalent circuit for linear mode, this one. And then we solve the circuit using M&A or loop analysis or whatever. And after that, we check the base current. Yes, we check IB. If it's flowing out of the transistor for an NPN transistor or into the transistor for a PNP transistor, that is, if IB is negative, then the BJT is in cutoff mode, and its actual base current is 0. That's right. By the way, its collector current is also 0 in that case. What's next? Well, then we have to replace the equivalent circuit that we had put there already by the cutoff model, and we recompute the circuit. That's what's next. How's that? We'll replace the transistor with this model, the linear one. We'll solve the circuit for this current, this one, IB. If that current is negative, like so, this is an NPN transistor, then the BJT is in cutoff mode, and we'll replace this linear model with this other model, with the cutoff model. And then we solve the entire circuit again. But what happens when the current IB is not negative? Well, in that case, if that current IB is a positive value, so it's flowing in the right direction, then what we do is we compute VCE, the collector emitter voltage. If that voltage is greater than 0.2 volts, the transistor is in linear mode. However, if that voltage is less than or equal to 0.2 volts, the BJT is in saturation mode. In this last case, we have to replace the BJT by its saturation model and recompute the entire circuit. Come again? Well, we compute this voltage here. You see, if this current is positive, we compute the voltage VCE, collector to emitter. If that voltage is higher than 0.2 volts, we leave the linear mode circuit because the transistor is in linear mode. It's working as an amplifier. However, if VCE is less or equal to 0.2 volts, we replace the BJT with this equivalent circuit. This one, the saturation equivalent circuit. And then we solve the entire circuit again. In a nutshell, with the BJT linear model, we solve the circuit. If IB is not positive, the BJT is in cutoff mode. If that current is positive, then we compute VCE and check that VCE is less or equal to 0.2 volts and the BJT is in saturation. Otherwise, the BJT is operating as an amplifier. It is in its linear zone of operation, in linear mode. And with this, we end the review of the essential facts. And now we move to a series of numerical examples that show the optimization of the operation point of a transistor. An example of a BJT biasing circuit. Here we see two sources, the AC signal source and the DC bias source. But the exercise is about solving the circuit in DC. In DC, the capacitors operate as open circuits, removing the right-hand side of the circuit and the left-hand side of it as well, leaving exclusively this part. So this is the part of the circuit we will concern with in this solution. The first thing will be to replace the transistor, this one, by its linear mode equivalent circuit, like so. We still identify the base, the emitter, and the collector. This is a beta 50 transistor for this exercise. Now we solve that circuit in assumed linear mode. Let's see, the base current is a current in an RV branch. Voltage of the origin 12 minus voltage of the destination is 0 volts minus the opposing source 0.7 divided by the resistance 400 kilo ohms, and that base current is 28 microamps, which is more than 0. What does it signify? That the BJT is not in cutoff mode. At least we know that, because the current in the base is not negative. But that leaves one open question to answer. Is it in saturation or in linear mode? To answer that question, we will need VCE, the voltage between the collector and the emitter. Because the emitter is at 0 volts, it's connected to the reference node. All we need is VC. And VC is the voltage of this node, 12 volts, minus the voltage drop in this 2K ohm resistor, produced by this current, the current in the collector. Let's compute that current in the collector is 50 times IB. We know IB. That current is 1.4 milliamps. Now that current will produce this voltage drop in this 2 kilo ohm resistor, and the voltage CE, which is just the voltage of the collector, is 12 volts, minus that drop, it's 9.2 volts, these volts, which of course is more than 0.2, and that has an implication. The implication is the transistor is in linear mode of operation, and this circuit really represents its behavior. The exercise does not end there. Let's compute now what is the power absorbed by this transistor. There is a little power absorbed here at the base emitter circuit, B emitter, which is IB times 0.7 volts. And there is some power also absorbed by the transistor at this CE port, which is IC multiplied by VCE. That is the power in the BJT. Base current times 0.7 volts plus 1.4 milliamps times the voltage, 9.2 volts VC. A total is approximately 13 milliwatts. That is the power absorbed by this transistor. There is more. We want to find the load line for this circuit. Well, what is this? You say, well, what I did there is just keep what we had in the previous slide for reference. The load line is a line drawn in the plane of I in the collector versus the voltage collector emitter. That is a line that hits the horizontal axis at VCC, 12 volts, and the vertical axis at 12 divided by 2 kilos, 6 milliamps. On that line, we will identify the Q point, the point of operation of the transistor. But we already know what is the current of the transistor at the Q point. We computed that it's 1.4 milliamps, and we know what is the VCE of the transistor at the Q point. We also computed that before. That is 9.2 volts. We have to mind the saturation line at 0.2 volts. And here we have VCQ is 9.2. Is the VC at the Q point. We computed that before, and the current in the collector at that point is 1.4 milliamps, which we will relabel as ICQ. That point is a little bit too close to the cutoff zone down here for comfort. You see, when we feed the signal into this amplifier, the oscillations of the signal will shift the position of that dynamic point up and down along this load line, and you see that it will hit the cutoff zone pretty easily. We would like it better if Q was to move closer to the mid zone between 0.2 and 12 volts, and that is what we want to happen. How are we going to achieve that? How can we move Q to the mid zone? You say, if only we had Q here somewhere in the middle, the current would be 3 milliamps instead of 1.4. Would be right in the middle between 6 and 0. Right. But for that current to be 3 milliamps around here, the base current would have to be 3 milliamps divided by beta 50. The base current would have to have been 60 microamps, this current here. But then we proceed backwards. For that current to be 60 microamps, because the voltage source continues to be the same, we'll have to reduce this resistor to what value? So we compute, we say that resistance, this one, will have to be changed for a 12 volts minus 0.7 divided by 60 microamps, 188 kiloohms. So if RB were 188 kiloohms, in that case, then ICQ would be right here, right in the middle, right here, 3 milliamps, and we will have an optimized Q point. And that ends this exercise. Now let's work on a second example, a circuit with a transistor in saturation. This is example B. It is exactly the same configuration we had in example A. The difference is the values of the resistors. This VCC source is 12 volts. We want to analyze the behavior of the transistor in DC. We want to know if it is in linear mode of operation or if it is in saturation or in cutoff mode. Well, in DC we know that those two capacitors will behave as open circuits and will eliminate the right hand side of the circuit and the left hand side of the circuit and leave us with this. As with the first example, we assume the transistor is in its linear mode to begin with, and we replace it with its linear model, this one. It's an NPN. I have identified the base, the emitter, and the collector. We'll solve the circuit the same way as before. The current in the base is in this RV branch, voltage of the origin, 12 minus voltage of the destination, which is 0 volts, minus the value of the source 0.7 divided by 400 kilos. That is the current in the base. Same as before, 28 microamps. Because that current is positive, the BJT is not in cutoff mode. We know that. The question is it in saturation or is it in linear mode? To answer that question, we need VCE. We need the voltage V between collector and the emitter. Because the emitter is connected to the reference node, VCE is directly VC. To find VC, we will need this current, which is the current in the collector. That is 50 times IB that we have already computed. And with that one, we'll determine the voltage drop in the 8.5 kilo ohm resistor. This node is at 12 volts above the reference node. Minus this drop will give us the voltage of C. Let's do that. The current in the collector is 50 times IB is 1.4 milliamps, same as in the previous exercise. The drop will be 8.5 kilos times that current subtracted from the voltage at the top node, and that tells us that the voltage C, which is just VC, is negative 6.25 millivolts. It's less than 0.2 volts, which is impossible. That is telling us in loud words that it's in saturation mode. Who? The transistor. The BJT in this case is in saturation mode. Well, if it's so, we need to replace the transistor with a saturation mode equivalent circuit and compute it all over again. There you go. The saturation mode equivalent circuit. We compute the circuit again. Of course, the base current will not change. It's still going to be 12 minus 0.7 over 400 kilos, 28 microamps. However, the transistor is not amplifying that current anymore. It isn't. So the current in the collector will be just the current in an RV branch. Voltage of the origin 12 minus voltage of the destination 0 volts minus the source in the branch 0.2 divided by 8.5 kilo ohms. That current is 1.39 milliamps. Even if we were to increase the current IB, you say how? Well, by decreasing this resistor here. If we were to decrease that resistor, the current IB would increase, but the current IC would remain the same. The saturation current of this transistor in this circuit. Let's compute what power that transistor is dissipating right now. Well, of course, the power will be the power in the base emitter circuit, current 28 micros times 0.7 volts, plus the power absorbed in the collector emitter port, 1.39 milliamps times 0.2 volts. That is 0.3 milliwatts. And that is the answer to this question. Let's work on this example where the transistor is in cutoff mode. This is example C. This is a common emitter voltage divider bias circuit. A what? A voltage divider bias circuit with a common emitter configuration. You say, well, wait a second. Bias circuit? What was a bias circuit again? The bias circuit was a DC circuit like this one here, whose purpose is to guarantee that the transistor is in its active zone and in its linear mode, to guarantee that this junction here is on and that this one is off. In other words, to ensure that in an NPN transistor this current is positive and that the collector is higher than the base. How does it do it? Well, this voltage divider will set a voltage here at the base that will push a positive current into the base, ensuring that the BE junction is on. At the same time, this voltage source will pull up the voltage of C above B to ensure that this junction is off. Oh, you say this is again? Yes, it's the voltage divider common emitter bias circuit, which by the way, it's the most popular of the bias circuits for the BJT. If you say, well, I see the voltage divider, you are dividing the voltage of the power supply 10 volts between R1 here and R2, and down here I see that, and that is the voltage you apply to the base of the transistor. What I don't see, you say, is that this is a common emitter. Why you call that a common emitter? Let's see. The phrase common emitter refers to the AC version of the circuit. In AC, the signal source, this one, is the one that is looking at the circuit. In AC, by superposition, we have eliminated the DC source. This source is 0, so that means that this is actually connected to the reference node, like so. So this resistor actually is in parallel with this one down here, and this is also connected to the reference node. But not only that, in AC, those three capacitors are like short circuits, like so. But then again, observe then that in AC, this shorted capacitor here is connecting directly the emitter to the reference node. It is bypassing this 2 kilo ohm resistor. So the emitter is connected through the reference node to the output load and also through the reference node to the input signal source. The emitter is common to the input and common to the output. That's why it's called a common emitter bias circuit with a voltage divider. But let's go back to the DC circuit, which is the one we need to solve today. We want to know if this transistor is in its linear mode, is it in saturation or in cutoff mode. So let me bring back the capacitors, bring back the source on the top and the other capacitor. Not only that, in DC we know that those capacitors will be like open circuits. We'll eliminate this load resistor and this signal source. This will be open, and this load will also not be there in DC or the input signal source either. Superposition, remember, we're solving the circuit in DC only. We're solving that in the bias circuit. Let's analyze this one. The first thing we do with this is replace the transistor by its linear mode of operation equivalent circuit, like so. In there I have identified the base, the emitter, the collector, the amplification of the current factor, the beta 200 IB, and the current of the base IB 0.7 volts. Here B is higher than E because I am assuming first and foremost that the transistor is in its linear mode. Later on we will find out if we were right or not. In this circuit, I find IB. How? Let me use M&A. First, an evil equation for this evil branch. VB is higher than the voltage of the emitter by 0.7 volts. Correct. And then a couple of KCL equations, one for the base node, currents going in, only 110 minus VB over 300 kilos over here, and that is equal to currents leaving, the evil current, the base current IB, plus the current through R2, VB over 500 ohms. And the other KCL equation for node E here, currents going in, 200 IB plus IB, currents leaving, only this one, V over 2000 ohms. We enter those three equations in the calculator, ask for those three unknowns, VB, VE, and IB, And we solve for those values and we concentrate on one value we need, the base current. The base current turns to be a negative number. That is all we care about right now. We say negative IB, that's impossible. That means only one thing, the BJT is in cutoff mode. That means that the currents in the base and the collector are zero. We need to replace the transistor by its cutoff equivalent circuit, like so, and solve the circuit again if we need to. What is the voltage of the emitter? Evidently there is no current here, there is no voltage drop there. The voltage E is 0 volts. What is the voltage of the base? Just a voltage divider, right? Right. And what is the voltage of the collector in this case? Because there is no current in the collector, there is no voltage drop in this 4.7 kilo ohm resistor. VC is just 10 volts. And that is all. The transistor is in cutoff mode. It's working as an open switch. Thank you very much.